The last topic I want to discuss in this chapter is relativistic energy. To set it up, let's imagine an experiment. What we can do is we can shoot a high energy electron at some target. Maybe this is a metal target. And so we shoot this high energy electron at this target, and it collides with an electron in the target, and it shoots that electron out. So what we'd really expect is the electron this high-speed electron that was incident on the target and our target electron, we would expect them both to come out on the right side of this target. That's what we would expect to observe. But instead, we don't all the time. We might observe 4 particles come out. We might observe the 2 electrons we expected, and also an electron-positron pair. Now, what's a positron? We haven't learned about that yet. A positron is a particle, and it is the antimatter version of an electron. So, electrons and positrons are antimatter pairs. They're identical in every way, except for the positron has a positive charge, and the electron has a negative charge. But they have the same mass. And so, what we see here is that the amount of mass we have in this situation just increased. We just got a positron and an electron out of absolutely nothing. That's super weird. Where did it come from? Well, it turns out that it came from the kinetic energy of that high velocity, high energy electron that came in and collided with the target. It came from the kinetic energy of that electron. So this is another one of the papers that Einstein published in 1905. He showed mathematically that energy and mass are equivalent. That energy is another form of mass, which is just crazy, right? Like, think about potential energy, right? How abstract is that? I just increased the potential energy of this piece of chalk. How abstract is that compared to the mass of this piece of chalk? The mass is how much stuff. Apparently, those are different manifestations of the same thing. That's really strange. To think about this, this equation, right? We've got our fast electron collides the electron at rest, but what we end up with is 3 electrons and a positron. That's pretty strange. Again, energy and mass are equivalent. And remember that C is a large number. So what is C squared? A really, really large number. In other words, a very small amount of mass can create a very large amount of energy. To turn it around, it requires a very large amount of energy to create even a very small amount of mass. So, in order for this scenario to happen, this high-speed electron needs to be moving very, very quickly. It needs to have a lot of kinetic energy. If it's moving that fast, it is a relativistic particle. And it turns out that we need a new equation, much like we did for momentum, we need a new equation for the energy of a particle if it's moving very quickly. So Einstein found that the total energy of an object of mass m moving at speed u is given by this equation here. Again, this is not a transformation of energy from one reference frame to another. Rather, if we know the velocity of some object in a reference frame, then we can calculate its total energy of a mass m moving at speed u. Well, what do I mean by the total energy? Well, if E equals mc squared and mass and energy are equivalent, then if I give this piece of chalk a toss, then it has kinetic energy, certainly, but it also has mass. And so since it has mass and kinetic energy, well, its total energy would be the sum of those two. So we call its energy that it has just because of its mass, we call that its rest energy, and then it also has kinetic energy. So the total energy will be the rest energy and the kinetic energy together. In order to figure out the kinetic energy, we need to take the total energy, as shown in the previous slide, and subtract away the rest energy. What's left will be just the kinetic energy. And we let this little symbol here, E0, represent the rest energy. So, mc squared is the rest energy, and the kinetic energy is K. That gives us our total energy. Okay, well, first of all, what is the rest energy of a 200-gram apple? Well, the rest energy is simply mc squared. And so then this is 0.2 kilograms times 3 times 10 to the 8 meters per second squared. And when I run my calculator, I get 1.8 times 10 to the 16 joules. And kind of hard to visualize a joule. That is a lot of energy. To put that in perspective, the chemical energy stored in 1 gallon of gas, and of course when we drive our car down the road, we're burning fuel for the chemical energy that's stored in it. So the chemical energy in 1 gallon of gas is something like 1.2 times 10 to the 8 joules. So, there's something like 100 million times more energy in the mass of an apple than there is chemical energy in a gallon of gas. So that's kind of crazy. How about its kinetic energy? How about the kinetic energy of this apple? Well, first of all, let's calculate gamma and see what we get. And let's just see if we might need to do a relativistic calculation or if we might get away with just the standard calculation that we did like we would have done in Physics 1. So recall that gamma is 1 over the square root of 1 minus u squared over c squared. And so plugging this in, 1 over the square root of 1 minus u squared is 50 meters per second divided by 3 times 10 to the 8 meters per second squared. You can try this. You run your calculator on that, and guess what you get? You get 1. It turns out that it's not exactly 1, but you got to go over there 14 decimal places to find a difference between 1 and the actual value of gamma. And so 14 decimal places, boy, we're not measuring the speed of this apple to 14 decimal places. I can tell you that. So for all intents and purposes, gamma is exactly 1 in this case. In fact, your calculator will just tell you it's 1. So if gamma is 1, we don't need to worry about a relativistic calculation for this apple. We can just do the kinetic energy calculation like we would have done last semester. K equals 1/2 mv squared. That is 1/2 times 0.2 kilograms times 50 meters per second squared. We run our calculator and we get 250 joules. Okay, so 250 joules of kinetic energy, 10 to the 16th joules of rest energy. Definitely this one dominates, right? So in the non-relativistic realm, objects will have much more rest energy than they have kinetic energy. Let's compare that with the electron, moving at 99.9% of the speed of light. So for the electron, again, for the rest energy, we're going to do rest energy. It's mc squared. 9.11 times 10 to the negative 31 kilograms is the mass. And 3 times 10 to the 8 is the speed of light. Okay, so now we run our calculator there, and we get, let's see, 8 times 10 to the negative 14. Okay, well, that's a small amount of energy, certainly, but we are talking about an electron, which has an itty-bitty mass. Okay, so That's interesting. Let's see, how about its kinetic energy? First of all, let's calculate gamma and see if this is a relativistic particle or if we can get away with a classical calculation. So gamma is going to be the square 1 over, the square root of 1 minus u squared over c squared. And we're 0.999 c. And our c's cancel. We're going to square it there. And so when we get gamma, we end up getting 22.36. Okay, so gamma is 22.36. Ooh, remember gamma for our apple was 1. Gamma of 22.36 means definitely relativistic. We definitely cannot get away with using our classical Newtonian equation for the kinetic energy. We need to use the relativistic kinetic energy. And so what we're going to do is we're going to do kinetic energy equals gamma minus 1 times the rest energy. Well, that is 22.36 minus 1 times 8 times 10 to the negative 14. So, what can we learn from this? Yes, these are small numbers. But the thing that I want to point out here is that for a relativistic particle, the kinetic energy is much greater than the rest energy. However, we found for a non-relativistic particle, the kinetic energy tends to be much smaller than the rest energy. So not only can particles be created out of energy, particles can return to energy. In other words, this E equals mc squared, it's not a one-way door. Particles, mass, can become energy, or energy can become mass. So anytime a particle and an antiparticle meet, they annihilate each other. What does that mean? It means that they destroy each other, and the result is just energy, usually in the form of a photon or multiple photons. So the mass disappears, and the energy equivalent of the mass is transformed into 2 high-energy photons. So we went from having mass, a physical, tangible thing, to pure energy in the form of a photon. It can go either way. What this means is that we need to tweak our idea of what conservation of energy means, because now the conservation of energy needs to include mass. Because if we don't include this E equals mc squared term, then we seem to have a violation of the conservation of energy here. We seem to have more energy afterwards than we do beforehand. But if we include the mass, we don't. We have exactly the same amount of energy before the collision as after the collision. So neither mass nor the Newtonian definition of energy is conserved. However, the total energy, the kinetic energy plus the energy equivalent of mass, remains a conserved quantity. And so here's some notation. Sometimes this can get a little abstract, but all this says is that the total energy before some event, any event really, must equal the total energy after that event. Which is the same as before. It's just that now we have to include the E equals mc squared term. This is how energy is obtained in a nuclear power plant. In a nuclear power plant, we may see this reaction right here. A high-energy neutron collides with some uranium-235. That creates uranium-236, which is highly unstable. Uranium-236 quickly decays into barium-144, krypton-89, and 3 more neutrons. And these three more neutrons are the chain reaction, right? So these can go now and hit 3 more uranium-235 nuclei, and this thing can really get going if you've got enough uranium-235 hanging out. So this is one possible path for this fission. And so recall that fission is the name we give when a nucleus breaks into smaller nuclei. And so this might be a reaction that you would see in a nuclear power plant. A very early nuclear bomb might have used this reaction. There's other ways for this to decay. This is not the only end of this equation, but it's one possible end of this equation. Now, what's interesting here is that if we were to add up the total mass here and the total mass here, we would find that they weren't the same. So even though if we counted neutrons, electrons, and protons, we would have all the same number of those things, right? It's not like we lost some of those particles, but it just turns out that this arrangement of those particles has a smaller mass than this arrangement of those particles. You know what? It's a tiny difference, but c squared is huge, so a tiny mass times a huge number can equal a significant amount of kinetic energy. How much? Mass is lost. Well, 0.186 U. Recall that U is an atomic mass unit. So U stands for AMU. And 1 AMU is 1.66 times 10 to the negative 27th kilogram. It's basically, but not exactly, the mass of a neutron. So that's so you can see that this is like 18% of an atomic mass unit, something like that we've lost. But where did that energy go? Well, it turned into high energy photons, which if you're in a nuclear power plant, then this energy can be used to heat water, turn it into steam, and run a turbine. So we can add up all of the total mass from the initial situation, and we can add up the total final mass, and we just see that they are not the same, right? Initially, we have one uranium-235 atom and one neutron. We add those up, we get this. At the end, we have one barium atom, one krypton atom, and 3 neutrons. We add that up, and we get something that is just slightly less. Our sun is powered in a similar way, except for in the sun, it's fusion, actually, instead of fission. So with fission, we're breaking large nuclei into smaller nuclei. With fusion, we're smashing smaller nuclei together to make larger nuclei. In the sun, it turns out that 4 hydrogen atoms get smashed together to make 1 helium atom. And the end result actually has a tiny bit less mass than the initial ingredients. What happened to that mass? Well, it turned into energy. And if you go outside when the sun is shining, then you can feel that energy hitting you. And so the next time you're walking down the street feeling that sunshine energy hitting you, think about the fact that 8.5 minutes ago, that energy was in the sun. And, it takes a long time for that energy to rattle around from the center of the sun. But not that long ago, that energy that's now warming you up actually was mass. It was literally mass that you could have held in your hand. And now you feel it warming your shoulders. That's pretty cool.